issue of the impact on the planet's angular momentum of the global warming process. So I'm going to start by showing you a few introductory slides by way of motivation. And then I'm going to talk to you about the theoretical basis of the work that I will describe, which is based on what we call the sea level equation, which basically describes in a detailed gravitationally self-consistent fashion the way ice and ocean and the solid Earth interact during a series of long time scale glaciation and deglaciation events. And then I'm going to focus on what I call the process of rotational feedback and the way in which the planet has conspired to remember the effects on sea level history that are associated with the feedback of variations in the centrifugal potential on sea level itself. That is, variations in the centrifugal potential that are caused by the ice age cycle. That is, the cycle during which water is exchanged continuously between water in the oceans and ice on the surface of the continents. And a lot of the story I'm going to tell you has to do with the GRACE satellite's measurement of time dependence of the gravitational field. So just a few comments by way of initial introduction. So we know, for example, that the global warming process is strongly northern hemisphere amplified. We think that much of this is a simple consequence of ice albedo feedback. There are additional processes involved. But basically the warming is strongly amplified in the North Polar region by about a factor of 2 over the mean warming of the surface of the planet as a whole. Happily, near the poles, we have pseudo-thermometers in the form of large accumulations of land ice on Antarctica, on Greenland, and also smaller accumulations of land ice shown here over the high mountains of Alaska. So these systems are well located to see the impact of warming at the poles. Of course, if they disintegrate, then there'll be a large redistribution of mass from the continents to the oceans, a large impact on the moment of inertia tensor of the planet, and an adjustment of the Earth's rotational state in response. Of course, if ice is lost from the continent, sea level will rise, and we're currently observing that rise of sea level using the Topex Poseidon and Jason 1-2 altimetric satellites. This is the earliest data set that was released based on Topex Poseidon. The more modern versions of this data set are much cleaner than this, but they basically show that observed altimetrically global sea level rise is going up at the rate of about 3 millimeters every year. So the focus of much of this work is on trying to explain which ice catchments are delivering this rise in sea level. One of the most important new sources of leverage we have on this problem is in terms of the GRACE satellites. This is a double bus which fly basically in almost polar orbit, inclination of about 89 degrees, at an elevation of 485 kilometers above the Earth's surface. The passive measurement that's made with GRACE is made interferometrically using a microwave link between the two buses in this two-bus train. And over a length scale of order 100 or so kilometers, this distance measurement is accurate to the width of a human hair. And what happens as the bus flies over a region like Greenland, which it sees to be losing mass, is that there's a slight fluctuation with each pass of the distance between the two buses, and that can be mapped directly into a time rate of change of the mass beneath the buses. If you look at raw GRACE data, and this is what I'm showing you here, in the top frame is raw GRACE data. These data have to be corrected for surface hydrology, basically the concentration of water in the top couple of meters of the surface of the continents. The dominant model for this hydrological correction is called GLDAS. we make this GLDAS correction to GRACE, and what you see happen is that if we zoom over the North American continent, we see three strong signals. The first of these is a signal which is expressed in terms of the equivalent time rate of change of the thickness of a water layer on the surface of the Earth. These three bullseyes, the main one sits right over, basically straddling Hudson Bay, and it consists of the implication of an increasing amount of mass under the satellites as it flies over this region. Because there's no ice, clearly, on the surface of the continents in that region, this is something else. And what the satellite is actually seeing here is the impact of the glacial isostatic adjustment process. In these four frames, there are basically four different fits of higher and higher order models to the GRACE data set. In the first fit, we're fitting just a mean and a single rate of change at each location. In the next fit, we're adding an annual cycle. In the next fit, we're adding a semi-annual cycle. And finally, an additional tidal influence. So what I'm going to be talking about next now is the theory for the explanation of this piece. And I'm going to use that theory to filter the GRACE field, not only over North America, but globally. And I'm going to talk eventually about the interpretation of these two negative anomalies, which are associated with the loss of land ice here from Greenland and here from the high topography of Alaska. So how do we explain this big red anomaly that sits over top of Hudson Bay on the Canadian landmass? This has to do with ancient ice age influence, the fact that the Canadian landmass was once covered at the last maximum of glaciation by a huge Laurentide ice sheet. At its maximum thickness, it reached about 4 kilometers to the west of Hudson Bay. And this ice sheet alone, to build it, required a drop in sea level, mean sea level, of about 80 meters. So there's a massive amount of ice that was collected in this region at the last maximum of glaciation, which is around, we think now, around 26,000 years ago. When this ice mass disappeared, sea level rose, and this is the best record we have available of that rise in sea level, which describes the exchange of mass between the continents and the oceans, which occurred subsequent to the last maximum of glaciation. The complete deglaciation event ended around 4,000 years ago. And you can see during that time, here's the last maximum of glaciation. Sea level rose by about 120 meters at this location. As it happens, and I'm not going to go into this in any detail at all, it happens that Barbados is perfectly positioned to provide an almost perfect measure of what we call the eustatic rise in sea level. That is the average rise in sea level that you would get if you did an average over the entire surface of the global ocean. Right? So this is an extremely important piece of observational information. So if I go back just one step, sorry. Well, the reason for the quality of that measurement is that it sits basically outboard of what we call the proglacial forebulge. When you load this region of the continent, the land sinks beneath the ice. It rises in the region surrounding the ice, right? And when the ice disappears, the land rebounds in areas that were once ice covered, sinks in the outboard region, and we're sufficiently far away at Barbados from this proglacial forebulge effect, we call it, that this measurement is especially insensitive to those edge effects, I call them, that are associated with the rebound process. So now the other curve I've shown you here, the red curve on the right, is actually a theoretical fit to the observations which are in blue, and I don't want to go into a long discussion of the coral-based measurements which underlie that Barbados record. So we need a theory to describe how ice, earth, and ocean interact during an event like this on very long time scales, and the basic ingredient in that theory is what I call the sea level equation. It's a construct of first-order perturbation theory, which has the form of an integral equation, which describes the relative rise of the the level of the sea with respect to the surface of the solid Earth. And in first-order perturbation theory, this comes in terms of the product of a function c, which is the ocean function, time and space dependent, which is unity where there's water and 0 where there's land. And the difference, this multiplies the difference between the geoid of classical geodesy, which is the surface of constant gravitational potential that overlaps the surface of the ocean in the absence of currents and tides. Right? Subtracted from this, then, in this representation for relative sea level history, is the time-dependent radius, local radius of the solid Earth. So in first-order perturbation theory, these two fields can be represented in terms of triple convolution integrals, which involve a Green's function for the difference between geoid and radial displacement, which is convolved with the surface mass load. That surface mass load has two components. It has an ice part, which is space and time dependent. This is the changing thickness as a function of space and time of ice on the continents. And it has an ocean part. And this total load, of course, has to conserve mass. And so this integral equation has an additive space-independent but time-dependent term, which ensures that all of the water which arrives in the ocean is just balanced by the amount of mass which is lost from the continents. So this integral equation is solved by unwrapping it on a basis of spherical harmonics. This is just linear field theory, right? But we have to solve this integral equation to very high at very high spatial resolution, and typically we unwrap this integral equation on a basis of spherical harmonics that's truncated around degree in order 512. 256 is usually good enough, but we can go higher when needed. And that's a consequence of the fact that the time dependence in this ocean function is absolutely critical. As you add water to the ocean basins, the oceans onlap the continents in most regions, and as you take water from the oceans and put it as ice on the land, the coastline actually varies continuously in time. So the critical piece that I'm going to focus on in everything that follows, aside from showing you how well this theoretical structure works, is on the adjustment we have to make to it to take account of the fact that as this mass exchange between land and sea occurs, there's a very large impact on the elements of the moment of inertia tensor of the planet. And this feeds back onto sea level through the variations in centrifugal potential that are caused by that changing rotation. So I'm going to focus on, how shall I say, the reliability of the Earth system recorder of this feedback process that's associated with the changing rotational state of the planet, which is caused by this exchange of mass between continents and ocean. This is, I hope, clearer to you than it is to me. I can't see a thing. One of the properties of the model that we have to be very careful to describe as accurately as possible is the input ice thickness history that goes into that integral equation. So in the first step in this sort of analysis, what we need to do is to prescribe a history of variation of land ice thickness as a function of time through at least one glacial cycle, which is about 100,000 years long. And on the land, on North America, for example, and in northwestern Europe, the constraints on that reconstruction are actually very strong, because we basically have deglaciation isochrones on the surface of the continents which tell us where the ice must have been during the deglaciation process. Right? And so what we can do is use the Barbados record to repartition back into the areas which are known to have been ice covered, mass in proportion to the area covered, to make a first guess at the ice field. There are certain properties of this, however, which are very tricky, and one of them involves Antarctica. The question as to when and how Antarctica actually deglaciated during this deglaciation event, how much ice came off the southern continent, used to be a major issue as to when this happened, and it's not such an issue now for for the reason of a piece of data I'm going to show you now. In the course of the U.S. Antarctic program, there's been a very significant drilling campaign carried out on all of the shelves around Antarctica to determine how and when the ice moved back from the shelf break during the deglaciation process. At glacial maximum, ice extended right out to the shelf break. As the system began to deglaciate, it moved back in towards its present location. So what we can do based on the sedimentary cores that have been drilled in the shelf is to determine the time at which marine sedimentation first recommenced during the deglaciation process on the shelf. These are just locations of known locations of ice fronts as a function of time. All I want you to focus on here are just these certain areas around the edge of the Antarctic ice sheet where sedimentary cores have been drilled from the ship. And I just want to show you what's happened here. You'll notice that basically this time of recommencement of marine sedimentation on the shelf fits this timing of what we call meltwater pulse 1b. And if we go back a little bit in the story, you'll notice in the Barbados reconstruction that there are two periods of time in which the ice melted very, very rapidly. The first of these occurred around 14,200 years ago, and the second around 11,500 years ago. The second of these is the one we call meltwater pulse 1b, and that fixes, those data fix the time of the main deglaciation of Antarctica to meltwater pulse 1b time. Just to give you an example of the quality of fit to a very large global distribution of relative sea level records, this doesn't look very clear to me. I hope it's better to you, but I suspect not. So I'm showing you basically 8 different locations, which are marked by the site names here, in which the theory has been fit to detailed radiocarbon dated histories of relative sea level change over the so-called Holocene epoch of Earth history from about 10,000 years ago up to the present. And you can see that in spite of the fact that the character of these records is a very, very strong function of location, this field theory fits those data extremely accurately. When the data correspond to the Holocene epoch, prior to the time when strong global warming began to hit the system. Let me show you the evidence in the sea level record for the influence of rotational feedback. If I go back this one figure again, what you'll notice in a very faint fashion on this picture is a red-red, blue-blue pattern that's superimposed upon this inner picture, which is the theoretical prediction of the rate at which sea level should be observed to be changing at any point on the Earth's surface where you could install a tide gauge and measure a secular rate of sea level change, right? So what you see imposed, sort of superimposed upon this complex global pattern is a red-red, blue-blue pattern, which has the form of a spherical harmonic of degree 2 and order 1. Pardon me?
How do you have that calibrated with the sea level in the middle of the land masses?
Remember, sea level in the theory is just the geoid, and the geoid is well defined even from the ocean onto the land. It's just an extrapolation, well, a theoretical extrapolation, if you like, of that surface of constant gravitational potential over the entire surface of the planet. So if you look, let me go back once more. One of the strongest imprints of this degree 2 and order 1 pattern you see right is focused right on the southern tip of the South American continent. So if we had relative sea level observations from along this passive continental margin, we might be able to see the direct influence of this rotational feedback effect. We have collected a huge database, in fact, of relative sea level histories from along this coast. And if you look at the comparison between the theoretical predictions of the model and observations, starting here north of the equator in Venezuela, and then ending up down near the southern tip of South America. Radiocarbon dated relative levels of the sea as a function of time reaching back into the past from now to about 10,000 years ago. The black curve is the curve with rotational feedback. We can clip that feedback out of the model and redo the calculation. The red curve is the curve with no feedback included. And what you'll notice is that as we go further and further down the coast, there is a more and more strongly expressed what we call a mid-Holocene high stand of the sea, a level that the sea occupied in the past, which is higher than present, which becomes higher and higher the further south you go along the coast. And in every location, it's only the impact of rotational feedback that allows the theory to fit the data. If you clip the feedback out, then there is no mid-Holocene high stand predicted at all. In fact, the levels that are predicted in mid-Holocene time are below the modern level. Okay? So this is a beautiful representation of the quality of the recorder of the Earth system of past variations in sea level over this range of time. Of course, yeah, anytime.
The greenest data.
The greenest data.
How come all theory go down at 10,000 years, but none of the data do?
Sorry? Many of these locations, all we have is the high stand. Right?
But how come high stand lasts all the way back to 10,000 years? Because
sea level is falling from the point of the high stand back to the modern level at present. Right? So the theory is constrained to the modern level now. Right? Okay? So if you look carefully at all of these data, you'll see some locations we have a complete set of inputs, other locations where we have only the high stand picked up. We never predict the high stand on the southern region of this coast in the absence of the rotational feedback influence. Okay? Sure.
Rotational effect seems to be required further down south, but if we look at the sites up north, it seems that the red curve is bigger better.
If you look here, we're north of the equator, and if you think of a spherical harmonic with degree 2 in order 1, there's a change in sign across the equator. Okay? So in fact, black is above red at all sites south of the equator. Red is above black north of the equator. That's because there's a sign change in the spherical harmonics across the equator, right? But in all cases, whether north or south of the equator, the model with feedback fits the observations best and rules out the possibility of models which do not include this feedback effect. So let me now go where I actually want to go. Okay? So here now is a prediction in multi projection, unwrapping the entire surface of the prediction of the time rate of change of relative sea level onto an ellipse with rotational feedback, clip it out, without rotational feedback, difference those two fields, and you see very clearly this spherical harmonic of degree 2 in order 1. Okay? If we now add to this field the theoretical prediction of the time rate of change of local radius, you can see the strength of this degree 2 in order 1 pattern in what we call the geoid. Okay? This is the time dependence of the geoid, and the issue is, does Grace agree that this is what the geoid looks like insofar as its time rate of change is concerned? So we have to further develop the theoretical structure in order to enable us to predict vertical motion, horizontal motion, and we can now compare having both vertical and horizontal motion predictions. We can, for example, and we've done a lot of this, use an array of radio telescopes in very long baseline radio interferometric mode, make predictions of the time variations in the baseline using these predictions of horizontal and vertical motion, or we can just take the prediction of the radial motion, add it to the predicted variation of relative sea level, the rate of relative sea level change, to generate the geoid field which I've just shown you. And the point is that if you include only ancient ice age influence, you see a geoid that's dominated very, very strongly by this degree 2 and order 1 pattern. Okay. Pause for a moment. Okay. Let's go back to the Grace field and use the theory now, which has been shown to fit the sea level record with very high accuracy, and use the theory to filter the Grace field to remove ancient ice age influence. So here's the prediction that I made prior to the time Grace flew. Okay. Here is the modification to the prediction that has been made by subjecting the ice thickness field to small variations in order to force it to conform to a very large number of vertical motion observations that have been made by GPS using GPS receivers. Okay? And you'll notice that this modification of the ice field now delivers this beautiful double bullseye pattern, which is seen by the hydrology-corrected version of the Grace observations. If we now simply do a full field subtract of the ancient ice age influence prediction from the full Grace field, then you see revealed the negative patterns, the negative bullseyes that are associated with ongoing ice loss from the continents. And we want to interpret these. And we can take each of these observations and map them in the case of Alaska, in the case of Greenland, and in the case of Antarctica into effective rates of global sea level rise. From Antarctica, we get about 0.35, 0.36 millimeters per year of global sea level rise, about 0.15 millimeter per year of global sea level rise from Alaska, about 0.6 millimeters per year of global sea level rise from Greenland. So this is what Grace sees. Here now comes an extremely interesting problem in the interpretation of the Grace data. We know we have ice being removed from the land. Large accumulations of land ice are entering the ocean. And Grace is supposed to be able to observe the time rate of change of mass in the oceans. So we look at the raw Grace data, and we interpret now the raw Grace data, and I'm showing you here the basically annual data over a period of about 6 or 7 years, both from the Center for Space Research at the University of Texas interpretation, from the GFZ interpretation at Potsdam, the second in the analysis centers. And what do you see in the Grace data in terms of the change of mass, inferred rate of change of mass in the oceans? Not only do the data suggest that the amount of mass in the oceans over this period of time is not increasing, but it actually suggests it's decreasing. This is a very bad thing. Okay? We know that mass is being lost from the continents. Grace says that it apparently is not appearing in the oceans. So what's going on? Again, we can use the theoretical structure and make a prediction of the error that you would make in the interpretation of the Grace data if you did not take account of the fact that during the deglaciation event of the last ice age, we added an effectively 120 meters of water to the global ocean. And the consequence of this is that the floor of the ocean is being continuously caused to descend as a consequence of the load that was added to the ocean basins at the end of the last ice age, right? This corresponds to a negative impact on sea level, which is huge, okay? Between 1.5 and 2 millimeters per year in equivalent sea level rise. Okay? So the extent of the contamination of the modern climate record as observed by Grace by ancient ice age influence is huge. Okay? So we can in fact close the sea level budget. If we take this contamination into account, we can add up the amount of mass which is coming off the continents, the rate of change of mass from the surface of the continents. We can compare that to the rate of addition of mass to the oceans according to the GIA corrected Grace data. And for the first time, we're actually to generate in terms of mass, demonstrate in terms of mass, that there is closure of the sea level budget. Okay? And this is something that's been hopelessly elusive, in the context of the IPCC work. But there's a rub here. And it has to do with the small ice sheets and glaciers' contribution to the rate of rise of global sea level. Although we know that we're getting contributions from the great ice sheets and from the small ice caps on Alaska, we have no idea where in an accurate sense, as to where the rest of the mass is coming from. And that's where I want to go to end this. Okay. And this has to do with Earth rotation observations. Ancient ice age influence, to which the glacial isostatic adjustment model is also tuned, right, causes two primary impacts on the Earth's rotational state that have been measured first by the International Latitude Service in terms of from about 1900 for about 75 or 80 years, basically by observing, using photozenith tubes, an array of photozenith tubes in the northern hemisphere, just observing star transits. And these data basically show a drift in the north pole of rotation, roughly along the 80-degree west meridian at the rate of about 1 degree per million years. Right? And that's picked up as a secular rate of change from the two components of the pole path, okay, which is dominated by this 7-year beat between the 14-month Chandler wobble and the 12-month annual wobble. Okay? So it's this secular variation that we're interested in, this long time scale rate of change. And the second element is what we call the influence of the non-tidal acceleration of the rate of axial rotation of the planet. Okay? This has been beautifully measured, actually, in lovely papers by Morrison and Stevenson going back 10, 20 years ago, basically by observing total eclipses of the sun and moon going back using naked eye astronomy from both China and Babylon, and inferring that the rate of variation of the length of day that one should be observing if tidal torque were constant, that there is a strong deviation from this. This is called the non-tidal acceleration in axial rotation. And this is, I've shown many, many years ago, to be directly associated with the rebound effect. Basically what happens when ice loads the poles, the shape of the planet is squashed, it's made more oblate. When ice melts from the poles, the planet then relaxes back towards a more spherical shape. And this is basically the cause of this non-tidal acceleration of rotation, which has been unambiguously connected to ancient ice age influence. Recently, however, it's become very clear that something has begun to happen in the Earth system, which is extremely profound in terms of variations in the Earth's rotational state. This is basically shown here in terms of the Space 2008 time series collected by Richard Gross and others at JPL Caltech. And what you'll observe in this, in the two elements of this polar motion time series, the x-coordinate, the y-coordinate, is that especially in the y-coordinate, and this is entirely expected, there is a knee in the rate of polar motion that occurs in the early 1990s, okay, in which the rate of polar motion decreased very rapidly, right, apparently over a shortish time scale. If we look at the complementary data set, in terms of the non-tidal acceleration of rotation, and this is data set from Cheng et al. At CSR in Texas, you'll notice here that there's an equally sharp knee at exactly the same time as we established here in a GRL letter that came out just a few months ago. This time of the early 1990s is about a decade prior to the launch of GRACE. Okay? So GRACE is observing the system at a time when the Earth's rotational state has undergone a profound transition, right, from a time in which its variations at secular rates of change were entirely explained by ancient ice age influence into a new state. If I compare now the prediction of the geoid that comes from the GIA model, glacial isostatic adjustment model of ancient ice age influence, to any one of the GRACE interpretations, you'll notice that there's a huge error, right? That if all that were happening in the Earth system were the meltback of the huge ice sheets that covered the continents at the end of the last ice age, we should be seeing, as I've shown you before, this hugely prominent degree 2 and order 1 pattern. We don't see it. What's going on? So the hypothesis that Scott Lutke and I made in a paper a couple of years ago is that this is a consequence, this misfit is a consequence of modern land ice melting. So in work that's just been completed recently, what we've done is to add to the glacial ice static adjustment model, not only in this picture, the melting event which is known to be occurring on Greenland, Alaska, and Antarctica as directly constrained by Greece, to make a prediction of what we would see in terms of the rate of relative sea level rise, if those were the only sources of melting occurring. What we've actually added are melt sources on the Himalayas, on the Peruvian Andes, and on the Western Cordillera, all of which are locations which have been identified in Dyarzhev's recent compilation of regions of strong land ice melting, and simply ask the question, if we insert these sources of land ice melting, can we reduce to an order 1, I call it conundrum. And that's basically what happens. Here is what we should see if all were active in terms of the time dependence of the gravitational field as expressed by the geoid. We should see this intense degree 2 and order 1 pattern in the geoid. If we add the influence of modern land ice melting, okay, then we correct this, this problem entirely. This is now, again, the Grace geoid, unwrapped in moleweed projection. And this is the new prediction that we make using the GIA model with modern land ice melting of geoid time dependence. So we think it's clear at this stage that the degree 2 and order 1 conundrum, if you like, that comes through the action of rotational feedback in the system is simply a consequence of the absence in the theoretical model of what we know very clearly to be occurring, which is very strong continuing melting of land ice, not only in the polar regions, but also on the high mountains in Asia, in South America, and also we think in the Western Cordillera. So this is a brief summary of the paper. This degree 2 and order 1 conundrum, as I've called it, has gotten to be a source of a great deal of interest over the past year or two, and I think it's very clear at this stage that that all we are seeing is an additional impact of the global warming process, which has now begun to disintegrate these large collections of land ice on high topography near the equator. Many of you will know, for example, that 2 of the main sites that we've looked at here are sites that Lonnie Thompson is focused on in his direct measurements of the rate of mass loss from these high mountainous regions. So I'll stop there now. I should have stopped 5 minutes early. Thank you.
Maybe you have just time for one quick question, and then we keep the question.
You are the sea level budget equation and the closed end budget is very important.
Yes.
Because the key part you think is DIA correction.
Yes.
The correction is 1.9 millimeter per year.
No, the number is actually, depending on the model, the number is between about 1.4 and 1.8, depending upon the model. I mean, my main point is that it's about a factor of 6 higher than the correction we have with the altimeter, which is a result that I published about 10 years ago. That the GRACE data are subject to a much, much larger correction in terms of the rate of mass addition to the global oceans than is the altimeter.
Certainly there. The second one is related to the ocean spheric rise. That part you use is only the ocean spheric and only surface layer.
Yeah, I mean, this is why I've just focused for the point for the purpose of this presentation on the closure of the budget with respect to mass. To get to the altimeter, of course, you have to add the helosteric contribution, which is between 0.3 and 0.5 millimeters per year, depending upon whose analysis you look at. So if you look at the 1999 paper that I published in 2009 paper, pardon me, that I published in QSR, there's a very detailed analysis there too about the way you get to the altimeter. And if you just focus on the ocean with the altimetric data, then again you get closure of the budget. So you can do it either in terms of mass by looking at continent compared to ocean, or you can focus entirely on the ocean and include the altimetric constraint.
Could you go back to the, I mean, first of all, compliments on the very beautiful balance of that. But, can you go back to where you had the overall budgets with the bottom of the oceans all falling out? And,
I've done something bad here. I have no way. I have no way of how to do something good.
I mean, there was one addition and one subtraction. They came out sort of within roughly airbags of each other, but
Yeah,
still, I mean, it's a sea level rising or sinking. You seem to be saying that the effect of
Sea level is rising. Absolute sea level is rising at the rate observed altimetrically. It's 3 millimeters a year.
Okay.
All right. The correction from mass in the global ocean that is observed by GRACE is very strongly influenced by the sinking of the ocean floor under the weight of the water load that was added to it during the last glaciation-deglaciation event. Okay, right? That's basically the physics. And this correction is huge basically because the density of the crust of the ocean, the surface of the ocean, is very high compared to the density of water. So you don't need to get it going down very rapidly in order to have a huge impact expressed in terms of the time rate of change of an equivalent water layer. Okay?
This effect, instead of having 3 millimeter rise, it have 5 millimeters? Is that
No. I mean, as I pointed out, I mean, if you just interpret the raw GRACE data in terms of the equivalent rate of sea level rise that should be occurring as a consequence from the change in mass, GRACE is saying that mass is not being added to the global ocean. Okay, right? This is the problem. So, and this is why the correction for the GIA influence is so important because, right?
doesn't rise? Because it goes into sinking of the bottom.
That's exactly correct.
Okay. So it does not rise.
No. This is no. You have to differentiate between the sea level variation associated with the change in mass and absolute sea level as measured altimetrically. So one is a mass measurement, and the other is a direct measurement of the height of the sea with respect to the center of mass of the Earth. So you need to be careful in differentiating these.
The mass is increasing, but it's going into the sinking of the bottom, not into the absolute rise.
It's relative to what you're talking about. I think that's the different. Yeah, it's relative to the Earth center or to the GOE. That's okay.
Why does try on the whiteboard maybe show the effects?
I think it's going to be a lot easier given the time to just talk about this.
Okay. So now when we keep the